All right. Hello, everyone. Welcome to today's installment of the Corundum developer meeting. Let me go ahead and get this show on the road here. All right. So, got a quick announcements and then status updates. So, the announcements, the next developer meeting will be on May 7th, and the next Switch developer meeting will be on May 14th. Um, I got the rest of the dates for this year down below for the Corundum developer meetings. All right. So, getting into it, just a recap on, deprecating the old repositories and the system verilog rewrite. I've been working on the new Mac, Phi, and GT wrapper that's coming together little by little. Um, Also, as part of the consistent transceiver latency stuff, I have to get some basically DDMPD components working on the FPGA to measure what the delay is. Um, so I've been doing some work on how to generate the some of the clocks required for DDMTD to work correctly, and some of that I've committed to the taxi repository. So I'll talk about that a little bit. I've also been working on the statistics collection subsystem. I've gotten the core of that ported over, and there's a few features that I'm thinking about adding to that, which I'll talk about in a few minutes. I'm also going to be integrating that into the Mac logic as well, which means that if you have a bunch of Macs step and repeat it in the design, you can then feed the statistics from all of those into a centralized counter module, which should be quite useful. Something I've been planning to do in Corundum for a while, but haven't really gotten around to it. But now that I'm um, rehashing everything, it's like, all right, let's take a crack at this. There's also another diagnostic protocol called QJTag that I'm starting to work on. I think I've discussed it a little bit previously, but the plan is getting a little bit more fleshed out now, so I'll talk about that. And then I also have the results from the initial measurements of the transceiver latency, so I'll present that at the end. All right. So getting into it. Um, Deprecations, I'm just going to breeze through this because I talked about it previously. Basically, all of the existing open source, progressively licensed code is going to be deprecated and superseded by the new taxi repository. So if you want development, so the all new development is going to be on the taxi repository, and I'm happy to provide paid support and paid licenses and such for that for the taxi repository because that will hopefully be, long-term commercially supported stuff. So if you like the stuff that I do and you want to see it, exist in the future and be maintained, buy a license and help contribute to that. All right.
Mhm.
So moving on. Oh, you have a question?
Yeah. What hardware do you support in the taxi at the beginning?
So right now I have a whole bunch of example designs for Xilinx devices, yeah,
Okay.
Ultrascale Plus. Um, I think
Yeah, you
once,
start on ultra scale, right? The
right, yeah,
minimum. Yeah, it's okay.
yeah. So I think once I get some of the reworking of the transceivers done, I'll actually be able to run on 7 series.
Okay.
The problem with 7 series, the problem with 7 series right now is they don't support the asynchronous gearbox mode, and all the
Mm.
Mac and PCS logic use the asynchronous gearbox mode. But if I switch to using, either the synchronous gearbox or raw mode, which I'm going to be doing for the consistent latency stuff, then it will work on some of the other devices. So
Okay.
that's the plan. Um,
Thank you.
I am going to be adding support for Intel devices at some point. It's more at this point a question of how to generate the hard logic portions of the design. So with Xilinx, there's a relatively easy way to do it with TCL, and you can just hand write some TCL that generates the core with exactly the settings that you want. With Intel, you can export a TCL file, but
You
I don't know
cannot
if there's
import.
like a yeah, well, no, I mean basically I don't know how version independent that is. Like it's a very big file with a lot of stuff in it, and it's like, okay, can we like pare this down to sort of a minimal subset that does exactly what I want and nothing more? Um, Not sure about that. It's not something I've looked into in great detail yet. Like with the Xilinx ones, you only need like, 10 lines or something to generate one of the GT cores, and that works. with the Intel parts, there's a bit more complexity there, and there's so many different tiles and whatnot that have different capabilities and such. It's slightly more complicated to support all those. So at some point,
Okay.
I'm going to circle back and put some more cycles into that and see if I can figure out a cleaner way of implementing that. Because so with the old permissively licensed repositories for all of the example designs, basically all of the transceiver wrappers and the TCL scripts and whatnot were all central or were all located within each example design. But what I'm trying to move towards is having maybe something that works a little bit more like the Xilinx cores, where you can just kind of have a just shared TCL files that are used by all the example designs and shared wrappers that are used by all the example designs. And then maybe have some parameters to configure stuff appropriately. Um, so there's less replication in the repository. It's a little bit easier to work with. And if I'm making a modification to something, I just need to do it on one set of files and it applies to everything. So um, I'm going to try to see if there's a way to do something similar for the Intel devices.
Okay,
Anyway,
thank you.
so yeah, for now it's the Xilinx Ultra Scale Plus. Um, and you can take a look at on the repository the list of the supported devices for example designs. And I don't think I have it ported to like literally every single board that I supported previously, but you know, eventually I'll end up adding everything, I think. Um, Now that everything's in one repository, I'm less opposed to adding an example design because it's like, well, I'll just have one copy in here and I don't need to maintain it across like five different repositories. So, um, yeah. Anyway,
Okay, thank you.
thanks for the question. All right, so moving on. So the system verilog rewrite. The plan is to rewrite basically Corundum and all the libraries in System Verilog and to place that under the CERN OHL strongly reciprocal license, such that I can actually offer paid commercial licenses, and that will go towards making this thing be sustainable in the long term. So I have System Verilog interfaces for a bunch of stuff. I have a number of components that have already been ported over. There's still a number of things that need to be ported over. I have the new Mac PCS and GT wrappers for 10 gig and 25 gig. Those seem to be working pretty well. There's a bunch of features that I'm planning on adding to those, which I'll talk about in a little bit. And I also have example designs for a bunch of different boards. Like I said, primarily Ultra Scale Plus right now, but I will be adding support for Intel devices at some point, and potentially Xilinx 7 series as well. I would add support for Versal if I had any Versal hardware, so that should be doable, but without hardware, I can't test anything. So, um, yeah, that's just I I put my foot down for Corundum, and I'm putting my foot down for Taxi Repository. I'm not adding support for anything if I don't physically own the hardware, at least in the upstream repository. If you want to maintain some support for some proprietary hardware separately, that's fine. We can discuss that. It just won't go in the mainline upstream repository. Um, because otherwise I can't maintain it. That's that simple. Um, all right. Okay. And I guess I'll breeze through this as well. System Verilog tooling status. It's improving in terms of the support and open source tools. Unfortunately, Icarus Verilog is not going to work. Verilator seems to implement System Verilog features a bit more completely. It's still missing some stuff, but it's at least usable. Versus Icarus Verilog is not usable for kind of the core stuff that I need. Um, with an old version of Avado or old-ish, it seems to work pretty well. I haven't tried with the latest version. I should just to make sure that they haven't added any bugs, which they probably have, but who knows. Quartus, actually, that reminds me, I still need to do a test with Quartus. It does build on Quartus Prime Pro, but it doesn't build on Quartus Prime Lite and Standard, which are basically everything other than the higher end parts and the Cyclone 10 GX. So Cyclone 10 GX is on Pro. Basically everything else is on Quartus Prime Lite and Standard. So that does kind of limit the device support. I have been looking at SV2V as an option for supporting Quartus Prime Lite and Standard, but there's a few bugs in SV2V. I think we got one of them fixed. I got to double check on what the current status is with that. Either there's some additional bugs in SV2V. I think there's also some bugs in Quartus that we're tripping over, which can potentially be worked around by SV2V, but we'll have to see about that. It might add a little bit too much complexity. But this is a potential solution for getting support on some of the older devices. Although I'm not a huge fan of, generated HDL, and this is generated HDL, so I don't know. Not optimal, but if that's the only option, then I guess that's the only option. Um, right, and also one of the big improvements with System Verilog is that it reduces the amount of typing that you have to do with connecting things together, and then also because all of the parameters specifying the widths and configuration of an interface gets rolled up into the interface itself, it reduces the opportunity for errors with hooking these hooking these parameters up wrong, which I've definitely done before, and that can be tricky to figure out. And also with the signals, it makes it, more difficult to hook something up wrong. Um, so this should make things a lot easier to work with. So at least in terms of the stuff that I've ported over so far, definitely seems like a pretty significant improvement using the interfaces. Although there are a few things that are a little bit tricky to figure out, and I've had to implement a few kind of workarounds, um, in relation to indexing across multiple interfaces and a few things like that. Occasionally, you have to unpack things, which is a little bit annoying, but it works. Um, all right. So as far as the overall porting process, most of the AXI stream stuff I have ported over. I got to double check what exactly is left. I think there's just a handful of things. Um, the AXI, I have AXI RAMs implemented, the tri-mode Mac modules, the 10 gig, 25 gig Mac modules, the PTP components, LFSR, UART, MDIO. Um, Part of the I squared C stuff, I think there's a couple more I squared C modules I need to port over, but the I squared C master is there at least. And I ported a bunch of XFCP stuff as well, so I can use that for debugging and diagnostic type stuff. I also need to port over the AXI crossbar modules, AXI adapters, DMA components, all the PCIe stuff, and I'm implementing some new synchronization primitives. I think I have one or two in there right now, but I need to implement, three or four more, I think, which should kind of normalize a lot of the timing constraints files. So it's like if you use like the reset synchronizer, then you pull in the timing constraints TCL's file for the reset synchronizer, and you don't need to implement, you know, kind of ad hoc stuff in different places. So that simplified some of the asynchronous FIFO logic and a couple of other things. But yeah, should be good once I get that a little bit further along. And I think there's a number of components that may no longer require separate timing constraints once I have the synchronization primitives done. Longer term to do, I want to implement a new UDP stack. Actually, I opened up a number of issues on the Taxi repository, including one for the UDP stack, um, as I don't really like a number of things about the design of the old one. So I think that can be significantly improved upon with a bit of rethinking at the architectural level. So um, I want to ruminate on that a little bit before implementing a new UDP stack because it would be useful maybe to have something a little bit more sockets like that's a little bit easier to deal with um, than the existing UDP stack where you have these separate header and data interfaces that are kind of limited and kind of restrictive in terms of what you can do. So um, people are interested in that, we can certainly discuss it. But yeah, that's kind of where we stand for the moment. Um, okay. So moving on to, right, I mentioned a little bit about the example designs. I have a bunch of designs right now for ultrascale and ultrascale plus devices in the Taxi repository. They're sort of kitchen sink designs that bring up a bunch of different peripherals. So they light up the Ethernet ports and the UARTs, basically relatively simple loopbacks that work well with the network tester, but are not so useful outside of that. You really want the UDP stack or something else in order to be useful if you want to plug it into a computer and, poke at it. Um, but without the stack, there's not much I can do. The eventual plan is to bring up like the external DRAM and add AXI infrastructure components and some other stuff to have, sort of more complete demo setups on all the boards. But yeah, for right now, it's just some of the interfaces. So to do Intel parts, I got to figure out the transceiver wrappers and TCL for setting things up. Um, I did implement the MDIO master, so the VC118 is now supported, which needs that MDIO init code. I need to port the I2C init code to bring up another couple of boards, as well as one of the FMC boards that I have that I want to add a couple designs for. So that'll be happening at some point soon. Um, but yeah, so things are coming together with respect to that, little by little. All right, moving on to the new Mac Fi GT wrapper. Basically, the idea is to build something that's similar to what I have in Corundum, which has not only the GT core and the Phi core, but also a bunch of additional supporting logic and control registers and things like that. So the new wrapper that I've put together, it actually uses the combined Mac and Phi logic. And I've added a parameter for simulation mode, so you can actually include that in the core logic of a design and then simulate it in place, as opposed to keeping the Phi stuff separate and um, having the XGMI connection, and then that maybe causes some problems in terms of being able to simulate the statistics connections and control connections and whatnot. Um, so this should be a little bit easier to deal with. Um, what I need to add next are um, some of the support components and DRP interface logic and things like that. Um, with Corundum, you have a relatively simple way of testing it because you got the PCI Express interface, easy to poke at stuff. So for the new wrapper, I need to implement some supporting logic first that I can use for actually poking at some of the internals. So long-term to-do for this, I need to make similar wrappers for the Intel parts. I need to support potentially some additional rates. It'd be useful to support 1 gig, be useful to support 100 gig, so I can have, a wrapper that has a CMAC in it that you can also run either, one lane at a lower rate or all 4 lanes separately at lower rates. Um, I'm also looking at supporting auto negotiation and SGMII, USXGMII for interfacing either with, plug-in modules that run at different rates or with Phi chips. Um, I'm also looking at integrating the statistics collection subsystem and then also the new QJTAG subsystem that I'm working on at a high level. So this will give you the statistics collection will give you monitoring basically, and then QJTAG will enable control of all of the internal transceiver registers. You can run eye scans that way, things of that nature. Once I get that all sorted out, and then also integrating the high resolution timestamping. So once I get the new time stamping, time synchronization subsystem implemented, that will also be rolled into the new wrappers as well. So you can just drop them down and then get all of these fancy features. Um, okay, so for the time stamping stuff, um, one of the things that's going to be very important there is getting DDMTD working. And DDMTD, it requires a reference clock that you're measuring against with a an offset, right? And this offset, it's basically one part in tens of thousands, basically. It's and the smaller that offset is, basically the more resolution you can get out of DDMTD. Obviously, there are some trade-offs associated with the value you pick for that offset, but obviously you have to generate that somehow. Um, a lot of the White Rabbit hardware uses a separate external VCO to generate this offset clock with software PLL or digital PLL. But what I figured out on the at least on the ultra scale devices is that you can use uh, the phase shifter built into the MMCM to generate this offset clock. And I have a little state machine which which can drive that. It's just a handful of lines. It's actually pretty simple, and it seems to work relatively well. The basic idea is that the phase shifter in the MMCM, you can request it periodically to shift the phase by one tap, either forwards or backwards, and the tap size is a VCO period over 56. So to shift by one cycle every you know 1000 cycles or 8192 cycles or whatever, you have to shift the phase shifter 56 times every, n VCO cycles to get this, either adding or removing one cycle every n. And the interesting thing is that offset ratio is applied to all outputs equally. So it doesn't matter what the divider setting you're using for the output versus for driving the phase shift clock. So if you use a smaller divider, so if you have a separate output for the phase shift clock and you drive that with a smaller divider, then you can potentially get better performance out of the MMCM phase shifter, as well as you can extend the frequency range that this is supported over. This is actually a problem that I ran into with testing this out on the FPGA. It wasn't the 1 gig version wasn't working, and eventually I realized it was trying to phase shift the MMCM too often because the frequency of the clock that was driving the phase shifter was too low. So if I increased that frequency, then it was actually working. So um, being able to separate this is kind of important. Um, with the current setup, I'm applying that phase shift with a very simple state machine that's just accumulating a numerator value into an accumulator, and then when it exceeds a denominator value, you subtract off the denominator and trigger the phase shift. And this will let you implement a rational fraction. Um, and that works reasonably well, but it does make me wonder if you might be able to do something like a delta sigma modulation on this and shift, forwards and backwards at effectively the highest rate that you can with the MMCM phase shift clock, if that makes much difference in terms of the overall performance. So there's definitely some more comprehensive testing that I think needs to be done in terms of this clock generation because there's many ways that you can reconfigure this, same 1 or 2 MMCM setup to generate these internal clocks, and it's a question of, what's going to provide the best performance out of DDMTD. And I'm not sure. One thing that I noticed as I was, rebuilding this test design and reloading it is that the even without changing the MMCM configuration, you could see significant changes in, the overall performance. So I'm not sure if that's related to placement and routing or something else, but that is potentially a little bit concerning. And with some of the changes that I made um, to the MMCM logic, it didn't really seem to have a significant impact on the performance. So what I think probably needs to be done is some more comprehensive testing, likely where we're actually dynamically reconfiguring the MMCM such that we're not changing the placement of anything. And that should give a better idea of whether or not, or which aspects of the configuration are, more important and what sort of configuration gives you the best performance. So one thing I did try doing is adding a second MMCM, and depending on the configuration you need on the first one, you can only, if you're going to generate both the reference and the offset clock out of the same MMCM, you have to use at least 2 channels, and only one channel has a fractional divider. So if you need a fractional divider, then you need a second MMCM to, get a second fractional divider. But also, if you have the second MMCM, then you can potentially down convert to a much lower frequency or try to use the smallest divider value setting to cascade at the highest potential frequency. Um, I tried both. I didn't really see any significant difference, but then again, I think maybe more comprehensive testing is needed where you can dynamically switch the MMCM between these different configurations without changing the placement to see if it's making much difference. So hopefully at some point I'll have time to sit down and take a look at this, or maybe we have somebody that's looking for something to do and might be interested in messing around with this a bit. That would be nice. We'll see. Um, right. So that's the MMCM side. And I've been using this for the phase measurements for the consistent latency stuff, and it seems to be working reasonably well. So, you know, we'll see. I was expecting there to be a bigger difference with some of these changes because my understanding is that the the cleanliness of the clock that you use for the offset is kind of important, but then as a result, maybe even using something from an MMCM wouldn't be all that great, but seems to be working reasonably well. I guess I also need to figure out how to do this on the Intel devices as well. Those also support similar phase shift capabilities, but there are some differences. I think the VCO tap size is a lot larger, so we'll have to see what the performance is like there. Um, yeah. So anyway, that's it in terms of the MMCM stuff. The other component that I've been working on as well is the statistics collection subsystem. And this is something that I basically put together for Corundum before. The idea is that you have these distributed statistics collectors which can accept, one cycle pulse and increment value type stuff. It'll accumulate that in an internal RAM and then periodically dump it via AXI stream, which you can then send through normal AXI stream muxes and FIFOs and such, and then accumulate that in a centralized counter module. And then that accumulates it into, BRAM or UltraRAM, so you can have, a very large number of 64-bit counters without having to run 32-bit or 64-bit AXI light all over the design just to read these counters. Um, but one thing that was a bit of a problem with the statistics subsystem is figuring out what the counters actually are, especially if you want to add additional counters in different parts of the design. So it got me thinking, along the lines of XFCP, where you can read out a little descriptive string, which then shows up in the software. Could you do something similar for the statistics subsystem? Well, I realized that, one LUT, that's 64 bits, either a 32 by 2 or 64 by 1, you can store 8 bytes in one LUT. So if you do like 8-byte strings, right, you have 8 bytes for, you have like an 8-byte prefix with each collector, and then another 8 bytes per statistic. That's actually not all that many LUTs. And if you implement something like that, then you can actually read out the statistics or the strings associated with each statistic. That could be, super convenient um, down the road as far as the overall design is concerned. So the question is, okay, how do we implement this efficiently? Um, well, one option that I thought of to save a little bit of additional resources is to use like a 6-bit encoding instead of 7 or 8 bits, which saves a few additional LUTs on top of that. So there's at least one encoding that maps rather nicely onto ASCII. And with using 6 bits instead of 8 bits, that, saves 25% of the logic resources to store that. If you take like so that the AXI stream infrastructure is transferring this increment value. Um, if that increment value is at least 16 bits wide, well, if you store two 6-bit characters, that's 12 bits. You still have 4 bits left over for, offset or something else. Um, and that is actually relatively efficient. So with this type of setup where you have to read out 2 characters at a time um, and transfer it, that requires at least 6 LUTs, right, in 32 by 30 in 32 by 2 mode. With that, you have enough room in 6 LUTs to store 8 statistics strings. So yeah, if you want to store 16 or 32, yeah, it would be 12 or 24 LUTs, but that's pretty small. And the idea is you send the string data periodically, and then basically have a little filter module which will extract that and expose it in some registers. So the idea is you can set the base ID and wait and see what shows up, read those values, set a different base ID, wait a while, so on and so forth. So it takes a little while to read all the string data, but it's very compact, doesn't waste RAM or address space, right? Because we don't need to store all of the strings in a block RAM that's mapped into memory somewhere where you can read it. Um, and it also works across like PR boundaries as well, right? So if you have your application logic and you add some statistics counters to it with the string support, then those will show up even if you're kicking the statistics up to a higher level module. Um, but yeah, when I started working on this, I ran into a very later bug related to parameter arrays. So I think I'm going to be setting this aside for a little bit until I can come up with a workaround for that bug. Is there a question?
Yeah, why string?
Why
Sorry, I
strings?
might have missed. Yeah,
Well,
some.
well, so the idea is that the statistics collector module, it just has a bunch of counters in it, right? So Like for example, you might use a URAM, which can store 4096 counters, right? So you have 4000 counters. What are they, right? You have a bunch of components that are generating the statistics data. Somehow you have to figure out, what those 4096 counters mean. So my thought is, well, is there a way we can have the hardware design just tell you, hey, this first statistics counter is, the number of packet drops, right? And have
Mhm.
this metadata
Why can't I
associated with the counters. Hmm?
why can't I have something like hex ID or something like, which are represented in binary format, and then I just the software knows, okay, which one is what,
I mean, you could do that, but then somebody has to assign those values, right?
right? Right.
And you have to keep track of that mapping somewhere. And if you want to add new values that aren't included in your list of IDs, like how do you do that, right? So, and if you're using those IDs, why don't you just use the
Strings.
just the index, right? It's
Yeah,
this
exactly.
this is
Yeah, yeah.
this is one of the things that I was trying to figure out in Corundum, and I didn't really have a good solution for it. It's like, okay, if we're going to add statistics counts for all the Macs, for example, well, where are they going to sit, right? What offsets are we going to use for that? What counters are we going to use for that? And if I update the design later to add more statistics or to move things around, how do we keep track of all of that? And I couldn't really think of any kind of clean way of handling that. But it's just like, well, hey, if we could, because the thing with like if you look at how the Linux APIs work, right? ETH is capable of extracting a whole list of statistics counts out of a device, right? So there's like a standard API for that. You can call it, it'll give you just a list of the counters. There's an associated call that you call it, it'll give you a list of strings that define what all those counters are. Um, so literally, that's how the Linux APIs work, right? You get the counters and you get strings that define them. So technically, you can put whatever you want in those statistics counters. They don't even have to be related to Ethernet. They can be anything. Um, you don't really need the strings, but without the strings, it's just a bunch of numbers, right? So I'm like, okay, well, wouldn't it be cool if we could implement the ETH API in a way that you could add statistics to the HDL and then just put a little textual description in there of what you want, and then have it show up in ETH right? When you run that command on Linux, even if it's inside of the application section or something and not part of the original logic, right? Because if you're using I mean, you think about how that process would work, right? If if you're using, let's say we have an upstream kernel driver, right? You can't change the driver. ETH is just asking the driver for the strings. Do you want to add a statistics point to this thing? How do you get the string data into ETH right? If you can't modify the driver, where do you store that information, right? Does it have to get stored in Flash and then somehow you have to read that out? But now it doesn't work if you load the design via JTAG, right? So it's like
But but
if you
but but in this case, I have the driver, right? So I can modify
well,
the driver.
right, but now you make a change to the HDL, you got to update the driver. You make another change to the HDL, you got to
Hmm.
update the driver. And this is one of the
Right,
things that I've been
right.
trying to avoid. Is like I want to totally decouple the driver from the design, right? So
Hmm.
I do not want to modify the driver for any reason other than I'm making some major architectural change. I'm changing the descriptor format, right? If I change the descriptor format, you have to change the driver. But if I'm changing the number of interfaces, well, the driver should be able to figure that out, right? If I'm changing the layout of some of the internal registers, the driver hopefully wouldn't need to access the internal registers directly, right? I'd want to use soft cores for that. The driver is just issuing a command to the soft core through you know a FIFO style interface sort of thing, and then the only thing that needs to know about the internal registers is the core, for example. So yeah, potentially you could have something where like that internal core would provide a list of strings to the driver, but that core somehow needs to know what that string data
Hmm.
is, right? So could the core read it out of Flash? Well, maybe, but then you have to write that into Flash somewhere. It's
Right, right.
yeah.
Got it.
So it's like there's other ways of doing it, but it's like the counters themselves are defined in the HDL. right? They are implemented on the FPGA, they sit on the FPGA. So wouldn't it be great if the FPGA design itself could expose this information in a
Right.
reasonably efficient way, right?
Right.
Because it removes all of the logistics of trying to keep track of this thing, right? If you try to add it to the driver, if you try to burn it into flash somewhere, now you have multiple pieces that need to be kept in sync. And then there's several
Hmm.
boards where you can't even access a flash from the FPGA, right? Some of the Intel devices, they have some Max 10 thing sitting in between. So you literally cannot read whatever you want out of the flash. So even if you said like, hey, we're going to reserve this region of flash for a set of statistic strings, on a bunch of boards that just wouldn't even work. So yeah, this I think is going to be a relatively nice solution that doesn't really add very much overhead to the logic, right? I mean, we're talking about like one
Right. Right.
LUT per point, right?
Yeah.
Which is not
Yeah. Yeah.
much. Well, and it looks like if you can use if you can fit 8 strings into 6 LUTs, then it's actually less than 1 LUT per point, right? So, you know, times a few thousand points, that's pretty reasonable, honestly, right? Because each of those points
Right.
is going to have to be generated by some logic, right? So there's going to be other overhead per point anyway. So, you know, um, yeah, I was thinking if you can get it down to 1 LUT per point, I mean, I don't think you can really get it much smaller than that. And then if you can put in arbitrary string data, well, now you're no longer limited by, some arbitrary, binary definition of what these parameters are. You can just put whatever you want directly in the strings, and then it'll just show
Right.
up. And I mean, this stuff is designed mainly for like debugging and diagnostic type stuff. So does
Right.
software have to be able to interpret these strings to know what the statistic is? Not necessarily.
Right. Right.
I mean, for some it might be useful, right, to pull out some of these various statistics counters for the Ethernet max and expose those, um, um, not necessarily by the ETH tool counters, but by some of the other counters in Linux that would potentially be useful. But the big thing is like, hey, you're building some custom logic in the application section, and you want to add a bunch of, statistic counters to it that are not related to the Ethernet max directly. Is there a clean way of doing that? And I think something like this could work pretty well and end up being a very convenient setup. That's one thing I've definitely noticed
Right.
with XFCP is that being able to just stick something. It's like with XFCP, I have an ID field, right? And yeah, I can assign IDs and whatnot, but just being able to whack a string in there and then you run the little enumeration thing and you can see exactly what the modules are or a little string. It's like it saves so much time. It's just so convenient to be able
Right.
to do that. Um, and the other thing
Right.
with the
Right.
statistics data is like well, with XFCP, like how many modules might you have on there? Like 10, 20, something like that. With the statistics, you might have 1,000 or 2,000 or something like that. There's a difference in the order of magnitude, right? Um,
Mhm.
and just the number of data points that
Mhm.
exist in there, right? And being able to keep track of all of those in an organized way, I think is super important.
Right. Right. Very nice chain of thought, actually.
Yeah. So I have a decent idea of how to implement this. Once I figure out how to work around this verilator bug, we'll see if we can get that implemented. And then yeah, that'll be super useful going forward. Yeah, and I was thinking about for the actually collecting these strings and making them available. I was thinking about rolling it into the statistics collector, the centralized counter module. But then I realized it might actually make sense to have like a little separate module that's also receiving the same AXI stream data but then the counter module just filters for the increments, and this module just filters for the strings. And then you can potentially drop down a couple of those for various reasons. So um, like the nice thing about the statistics counter module is that it's read only. So you can have multiple components poking at that and nobody's going to step on each other. But with this reading out the string data, that's a slightly different animal because you basically have to set, what little range you want to look at, wait for those strings to
Hmm.
show up and then read it out. So if you have multiple
Right.
modules all trying to read the strings at the same time, you can have a problem. So
Right.
like let's say you wanted to have the statistics subsystem available both via PCIe and via XFCP, for example, you might want to have multiple modules for reading out the strings that are separate. Yeah, I haven't also figured out necessarily if that's the best approach for reading out the strings, because another option could be just a FIFO style interface, right? You just capture all the string data and then you just read that out periodically. There's several different ways of doing that. I haven't I haven't determined what's going to make the most sense, but you know, it's um, it's a work in progress. I think the getting the collector end figured out first and how to transfer that string data up through to the central collection point is the most important thing. Then the next thing is to figure out, okay, how do we properly expose that? Um, and the other thing is that it might take a little while to read all these points out, but it's like with the driver, you can spin up a, background thread or something which can collect all of these over, over a few seconds or whatever, which is fine. You know, yeah, it adds a little
Right.
bit of complexity, but doesn't really affect the performance at all. So
Hmm.
this is one of these things where it's like you got to find the right sort of balance. Like I think it's potentially going to be super convenient. It doesn't need to be very high performance. Question is, how do we do it with low overhead, right? We don't want to add a lot of
Right.
logic resources to make this work. So
Right.
so yeah, I'm not sure I have it totally figured out yet, but it's looking pretty promising. Yeah. So that's the statistics subsystem. Like I said, I have um the core components ported over. I'm working on the string thing. Oh right. And I'm also working on integrating it into the Mac modules. So basically, the idea is that for the Ethernet Mac modules, there'll be a statistics clock input and then a streaming, output for the statistics increment data. And then you can set the base ID for that module. So if you have multiple Macs, you can set the base IDs different such that they all get a different set of counters. Um, and the idea that I have is to support kind of several different levels of collection where you can specify like level one would give you 8 counters, level two would be 16 counters, so on and so forth. Higher level means you get more counters that, cover more stuff. Um, and I'm working on this. The status is that I'm adding more outputs to the Mac modules right now that can be fed into the statistics collection subsystem. And eventually, once we get the strings sorted out, then that'll be rolled into this as well. So when you drop a Mac down, I'll probably actually have an option for that. Do you want strings or not? So if you turn the strings on, then you would get all the string data as well. And this is kind of my initial set of statistics points. I may shuffle some stuff around between the different levels, but it's like the first level you get RX and TX packets, bytes, FCS errors, underruns, FIFO drops, um, fragments, jabbers, that sort of stuff. Level two gets you this is kind of a standard um, histogram of packet sizes. So, you got off the bottom, off the top, and then 64, 128, 256, 512, right? Your different packet size bins. Level three extends the histogram by a few bins and then gets you unicast, multicast, broadcast, VLAN, pause frames, PFC frames, um, and a few other errors. I'm wondering if maybe it makes sense to put some of these errors over here and then take like fragment and jabber and move them down. I'm not 100% sure. But this is kind of relatively rough. I'm mainly just trying to figure out what do I need to do in some of the core Mac modules to collect some of this stuff, right? So it's like for the histogram, we just need the packet size, and then that can be the histogram can be computed after the fact. Um, multicast, broadcast, unicast that involves just a couple of additional LUTs to look at the address at the start of the packet. VLAN, same kind of thing. Some of the stuff we already have outputs for, like the control frame stuff. That's for both pause and PFC. Basically, I have outputs for that already. Um, so yeah, there's actually just a handful of things that I think I'm going to need to add. But yeah, that's the first step is to implement all of the basic functionality needed for this. Um, and then once we have the counters figured out, then I can get that all rolled into the existing Mac cores and wrappers and whatnot, and then that'll be super convenient going forward. All right, so that's that. Now I'm also starting to take a look at so the statistics collection is good for monitoring, but if you want to control a bunch of components on the device, especially, somewhat out of band, say, or in kind of a diagnostic application where we're not talking about like a NIC here, we're talking about just a design running on a board sitting on a desk or whatever. Is there a nice way to do that? So I have XFCP that I've used in the past, and I've been using that for some of the tests, but what I've been looking at is something that's more of a design in debug diagnostic sort of thing. Like XFCP is good if XFCP is in charge, but let's say you take something like Corundum and you want to be able to have some diagnostic subsystem that can, talk to the transceivers, talk to like the DDR MIGs and a few other things in a way that you can just set it and forget it. It's just designed in as part of the system, and then it's there when you need it to debug stuff. XFCP is not particularly a good option for that. It's higher overhead because of all the packet switching infrastructure. Um, it has its advantages, but it's not optimal for this sort of thing. So the idea that I came up with is to basically build on top of JTAG. So I did some work with the QSPI flashes, and it's like, well, the cool thing about QSPI is that effectively it starts out in SPI mode, and then based on the command that you send, it will switch into QSPI mode, where it will use more pins to transfer the data more quickly. So that's the idea with QJTAG. It starts out in JTAG mode, but then you put the whole chain in bypass, and hey, now you have a 4-bit or 8-bit parallel bus. Well, that's like AXI stream, but without the handshaking. So now you have a 4-8-bit bus. You can just send whatever command you want, and you can transfer data much more quickly through it. And the cool thing is that if you put the whole chain in bypass, hey, you can put regular JTAG devices on the chain as well. Yeah, you need to add a couple of flip-flops in parallel with the device to expand the TDI TDO, but that's not a big deal. And then with QJTAG, the idea is that you can run it in JTAG mode. So if you build a JTAG chain, you can talk to QJTAG devices as well. Um, and the plan here is to basically build this for specifically, register and memory read-write type operations. So it'll be a relatively restricted protocol. You can't do whatever you want. But then I'll build shims where you can inject read and write ops into AXI Lite interfaces and AXI interfaces, things like that. So if you have an AXI crossbar at every single output port, you can have a QJTAG shim that all sits on one chain, and then you can just go through and, poke whatever's below that, right? Do we have MIGs? Do we have, register spaces, whatever? You can do all that without having to add a whole parallel interconnect. And then also for something like talking to transceivers, those might be spread across the entire device. JTAG might run at 5 or 10 megahertz or something. That's pretty slow. You can run that pretty easily across multiple SLRs and have everything work. And the other thing that I want to do with QJTAG is support having components sit on multiple chains, so you can have one long debug chain that hits everything, plus internal chains that are driven by internal logic for register operations that you might be controlling that from a soft core or from PCIe config space or whatever. So um, right, and with QJTAG, I want to support several different ways to control it, right? If you can control it via JTAG, you can put a physical JTAG port down, you can plug in a JTAG cable, control it that way. There's code for a little shim that sits in PCI Express config space that can be used for driving JTAG scan chains. I think somebody integrated this into Corundum a while ago for talking to like a RISC-V soft core, so you can debug the soft core via PCI Express config space. So hey, if we can connect that up to QJTAG as well, that would be very cool. I'll implement a UART bridge and XFCP bridge, so you can just plug in via to a board via UART, talk to the chain that way. And then also what I want to implement is a module on the FPGA that can implement AXI Lite or some similar register style interface where you basically have an address reg and a data reg. You can write, I want to access this address and I want to write this data to it, and then that module will take care of driving the chain. So that whatever software you have, it just sees address reg, data reg. Doesn't the implementation behind that is not relevant. So what you can do with this module is if you have like 4 devices sitting on the QJTAG chain, you'll have 4 address registers, 4 data registers. You can send whatever you want to any of those interfaces. And this basically will replace things like AXI Lite interconnect infrastructure for register access applications. I'm also thinking to have per instance strings like XFCP, so you can go through and enumerate exactly what all the components are. I was also thinking one of the cool things about XFCP is that it's hierarchical. With JTAG, it's a chain, it's not hierarchical. But if you have a list, there's ways you can kind of annotate it to turn it into a tree. So if this is technically a tree, in terms of how the modules are organized in the HDL, well, hey, can we allow software to extract what that tree is? So you can actually have a nice tree um, when you enumerate the chain. And I think there's definitely a way to do that by adding some effectively hierarchy markers. I need to figure out the details, and there is a question of trade-offs. If we're adding additional stuff to the chain, that's going to reduce the performance and increase the latency. So I'm not sure necessarily if that's the only way to do this. I got some ruminating to do, but if it works, it could be a pretty neat little setup to enable extracting a tree, because that was one of the things that I like about XFCP is the hierarchy. If you can get that working in QJTAG, that would be really cool. So here's just a very basic block diagram of what I'm talking about here, right? You might have a top level JTAG port or bridge device that can be hooked up to a big long JTAG chain that hits everything, including like soft CPUs and other stuff. So you can use that for, top level debug. And then internally, you can have a couple of, AXI light modules, which have, address and data registers, very easy to interact with software running, on a soft CPU or on PCIe or whatever. And then this one can then interact with other QJTAG components internally. So this interface here might be just 1 bit wide. These might be 4 bits or 8 bits, so they can run at a higher level of performance. So with this setup, you can use this JTAG interface to, do iScan, for example, on the GTs while the design is running, completely independent of whatever the design is doing. Another option is you can access this DRAM here without having to add an additional, AXI crossbar port or crossbar or something to get access to this memory here, which is otherwise dedicated to some internal logic. So I know for Corundum, something like this could be useful where you want to access, the DDR MIGs on a Alveo U200, which are otherwise dedicated to, some internal logic. And maybe you don't even have an AXI crossbar in that instance, but you still want to have, some capability of poking at those MIGs and seeing what's sitting in that DRAM. So that's kind of the idea. I still have quite a bit of work to do to get this to a state where it's actually working. I've implemented like a JTAG tap module, but there's a few more odds and ends that need to be sorted out before this is actually going to work. But I think it's a pretty promising idea that's going to be quite useful going forward. And the plan is to integrate it into all of the Mac wrappers. So if you drop a bunch of these down on the device, you can talk to all of them very easily. And then because you can also access this like from a serial port or from XFCP, I will be updating all of the example designs such that you can use this on everything that has a serial port anyway. And then you can run iScan, you can change the transceiver rates, you can do all sorts of fun stuff like that, and really exercise all the capabilities of the Mac and PCS modules um, with this subsystem. So yeah, that's going to be pretty cool going forward. All right, so now last thing to talk about here is the transceiver latency stuff. So what I've done, well, let's see here. So the idea is that I need to figure out how to configure the transceivers, not so much to get the lowest possible latency, but to get consistent latency. And this is to support the time synchronization applications. Now, most likely, this is also going to be a very low latency mode of operation, so that should definitely shave off a few nanoseconds of latency, both coming and going for all of the Ethernet interfaces, which there's some people that care very deeply about exactly how many nanoseconds it takes to get something onto the wire or off the wire. So that could be useful going forward. But yeah, the main thing is to
That
figure
gets
out.
you paper.
Well, I don't know, but it gets you a certain type of paper, right? Not necessarily research papers, but something maybe more valuable from depending on your point of view, right? um, yeah. Anyway, the idea here is to figure out what configuration to put the transceivers in, right? So what stuff needs to be bypassed, what stuff can be used in order to get the performance that we want. And as part of this, it's one thing to mess around with the transceiver configurations in Vivado and to look at the documentation and whatnot, but ultimately the ground truth is to actually run these transceivers on a board and see what the performance actually looks like. So I put together a test design that put down a bunch of GTYs and DDMTD modules and XFCP on a VC118. And then what I can do is with multiple transceivers and multiple configurations running at the same time, as I can then run some slightly long-term tests, reset things several thousand times and see what the latency looks like. So I put down 4 different configurations: 1 gig 20 bits, 10 gigs 32 bits, 10 gigs 64 bits, and 25 gigs 64 bits. And these are all the internal clock frequencies for all of these. These are all just, they're running in raw mode, right? So this is your standard 25 gig line rate over 64 or over 32, or it's like your 10 gig rate over 32, or 10 gig rate over 64, 10 gig rate over 32, and then this is your 1.25 gig over 20 to get the 62 and a half. So the question is, with DDMTD monitoring both the transmit and the receive phase offset, and also with a little bit of additional logic to figure out what the barrel shift is, what does the latency variance look like? And these are the results that I collected. Basically, what these represent is we take the measurement, or the what we get out of the TX side DDMTD, the output of the RX side DDMTD. We take the difference between those, and then we also subtract off the bit offset, which is, I have a little bit of additional logic to figure that out. Basically, on the transmit side, I'm sending PRBS, except I take the highest bit and set it to the inverted version of the next highest bit, which effectively does the same thing as the 6466 sync headers. And then on the receive side, I have a little bit of logic, which is just looking for differences between adjacent bits. And wherever we are seeing consistently on every cycle a difference between the 2 adjacent bits, that's where the barrel shift has placed us. So you can figure that out based on the bit position, and then rescale that based on the, that determines how many degrees of phase shift effectively we need to remove based on what the serializer did. So yeah, you make that computation, and that gives you the offset, and then we repeat this several thousand times. We reset the TX, reset the RX, rerun the measurement times all of the channels on there, and this table represents basically one of those measurement runs. We get similar results with a loopback, or with electrical loopbacks, with active optical cables, PSM4, CWDM4. I haven't seen any major differences between things. In a couple cases, there has been a lane or two that's less reliable, but whatever. We can take a look at that later, perhaps. But one thing I did notice is that the values are not as stable as I would like across builds. So they seem to be relatively consistently the numbers that I have here, approximately, but sometimes you'll have a channel that's like 2x what the number is here. So I don't really know what's going on there, if this is something placement related or if there's something else going on. And it's also unclear how much of the variance we're seeing here is from DDMTD versus, whatever is inherent to the transceiver itself, because obviously there's some stuff going on in the transceivers on the TX side to do the buffer bypass, and on the RX side, you got the buffer bypass. Potentially there's something going on there, plus the CDR logic that's potentially going to be moving stuff around too. So yeah. The interesting thing is the performance on the TX side seems to be getting slightly better with increasing link rate, but the RX performance seems to be doing the opposite. It seems to be getting worse with increasing link rate. So I mean, I guess that probably makes sense in terms of what's going on the physical link with the higher speeds. Maybe it's getting more sensitive to the to any jitter on the line. Um, and then on the transmit side, the higher clock frequency maybe is a little bit better in terms of whatever logic is taking place inside for doing the buffer bypass. Um, I'm not sure. I think there's definitely room for improvement here. Um, but well, and let me think here. So I think the conclusion here is that there's definitely room for improvement, but I think this is probably probably the best transceiver configuration to build on top of, right? Because we're actually getting consistent results here in the picoseconds. We don't have stuff wiggling around by, a whole clock cycle or something, um, or a significant fraction of a clock cycle. So yeah, as much as I would like to get like the range below 10 picoseconds for everything, that might not be feasible. Um, and standard deviation of the offset being up in 10 12 picoseconds, assuming we can get that reliably, that's actually not bad. Now I did actually see a paper out of CERN talking about how to get the transceiver latency down to, or the latency variance down to like a picosecond per channel for both the TX and the RX. um, it seemed like on the TX they had a slightly different approach, where instead of putting it in buffer bypass, they used the transmit phase interpolator and played a couple of tricks. Um, so that I could potentially look into doing that at some point. One thing I realized also looking at the documentation is that you can't use the TX phase interpolator above like 16 gigabits per second. So it might work at 10 gig, but it wouldn't work at 25 gig, which is um, rather annoying, but it is what it is. So it seems like that particular technique maybe would only work at 10 gig and below. And then it seems like on the RX side, there may not be a really clear way for um, improving the situation. Now, one thing that I'm not sure about at this point is what other options there might be on the RX side. Um, if you're doing something like White Rabbit, where you're actually synchronizing the links and you're bringing it to the same frequency, it potentially means that you could run the CDR effectively open loop and do something different in terms of how that thing is being driven. I'm not sure if it's possible to do that for the ultra scale devices. I'm assuming it probably is, assuming you can figure out what register to poke via DRP. I did see somebody talking about, I think for a 7 series, that there is a particular DRP register where you can directly control the the RX side phase interpolator. So potentially something like that could be done for Ultra Scale Plus. Um, and again, this would probably only work for running, with White Rabbit in a synchronized system. If you wanted to do something like PTP, where it's not synchronized but still get the high resolution timestamps, you might not, or you probably wouldn't be able to use that technique. Um, so that might be worth looking into at some point. I guess if you did go that route, the question is where would you get the feedback from? Um, that I'm not sure about. Um, I guess one of the reasons I was looking into that is I might need to do something like that for trying to run the 10 gig transceivers at 1 gig. If the feedback of bit position doesn't work quite right, due to the relative timing of things, then you might need to run that open loop. Um, but I might have to cross that bridge when I get there a little bit later, at least in terms of 1 gig support for running at the higher rates. Yeah, I guess we'll have to see. But yeah, so I think for the time being, what I'm going to do is set these measurements aside, but use this particular transceiver configuration um, for the Mac and PCS logic going forward, and rebuild things to work with this particular configuration. Because I'm not sure. I think to do a lot better than this, it's going to take significantly more engineering effort. And this is definitely a significant improvement over the current setup. So that's about all I got in terms of the latency stuff. If anyone has any questions or comments, feel free to fire away.
So I wanted to ask, so is the QJTAG stuff,
Mm-hmm.
it's independent of Corundum, right? So are you going to integrate into the same code base, or are you going to just spin it off as a different repository altogether?
Oh, it's going to be part of Taxi. It's going to be used in all the example designs, and it'll be used in Corundum.
Right.
Basically,
But
just like
but
just
but that's it's a independent stuff, right? I mean, doesn't necessarily need to be in the code base, right? Or are you building some support which requires
well. So the idea is that
certain things?
I'm going to put everything in the Taxi repository, right? So I can use it in the example designs and whatnot.
Hmm.
It's basically the plan that I have is to make QJTAG and the statistics subsystem basically features of the Mac cores themselves, right? So if you're using a bunch of those cores in your design, well, instead of trying to figure out how to handle all the statistics yourself and hooking up all the control registers yourself, I can just string up QJTAG in the statistics subsystem, and now it makes everything a lot easier to use.
Hmm.
It kind of takes care of all that infrastructure for you. Because that's
Right.
the so that was one of the things with XFCP. It's like there are a few situations where it's like, ah, man, it would be nice to have the XFCP logic in the same repository, and I could just use it for this or that or the other thing. So with Taxi, since I'm moving to using, since it's a new repository, I'm just like, okay, I'm just going to put everything in there: XFCP, QJTAG, statistics stuff, AXI stream, pStage, everything in one repository. And then it makes it a lot easier to cross-pollinate stuff. Because with the
Hmm.
old setup where I had all these repositories, there was a fair amount of code that was copied into multiple repositories. Like some of the,
Hmm.
um, I think there's a couple of repositories that had copies of the AXI stream FIFOs. There was multiple repositories that had like the arbiter logic in there. So it's just like, this is not the best way of doing things. So by putting
Right.
everything in one repository, that simplifies stuff. Um, And then with Corundum, that will probably be a separate repository. But there is a question of, a lot of the code written for Corundum may actually end up living in the Taxi repository instead of in the Corundum repository, right? Because if it's something specific to Corundum, okay, that goes in the Corundum repository. But if it's something that's not specific to Corundum, maybe it's general enough to go in the Taxi repository, right? So it's
Hmm.
like, for example, if we're going to write a new UDP stack, there's probably going to have to be modules for computing checksums, for example.
Hmm.
Well, do those go in Corundum, or maybe those are general enough to just be used as part of the UDP stack and then do double duty, right? So that's stuff that I need to figure out. But yeah, I'm definitely going for a more integrated approach because I think that's just going to make things easier to use.
Also, I just have a very specific question. So, in in the K26 SOM module, right?
Yeah,
Uh, there are four GTH lanes, and each of them can do 12.5 G bits per second.
yeah,
So, does that mean it can do 25
no.
gig? Why?
12 and a half is less than 25, right?
But I have four lanes, right? So I can use two for RX, two for TX. No, that's not how it works.
Well, okay, so by lane, each one of those lanes is a TX and an RX, right? So you got four TX and four RX. But yeah, so well, how would you combine two lanes? You get 25 G, how would you
Uh,
combine two lanes?
so like I thought how you usually break out stuff from a QSFP or something like that. You kind of choose lanes and you decide to do, okay, for four lanes I do 25, and then another four lanes I do 25 gig, something like that sort. So I thought you can also merge otherwise as well. No.
Well, so a QSFP DD has a very complicated PHY retimer repacker chip in there that can do a lot of stuff. Um, so with a QSFP DD, yeah, you can pick, do you want PAM4, do you want NRZ on the electrical side, and then the PHY chip in there will do the
Hmm.
correct transformation. But for 25
Hmm.
gig, we're usually talking about an SFP28, which is one lane at 25 gig.
Right. Okay.
I don't think there's any standard way of interfacing two lanes at 12 and a half to one lane at 25. And also it's not 12 and a half, it's like 12.89 or something. So
Okay.
if the spec in the Xilinx datasheet is really 12.5, 12.89 is outside of that. So that wouldn't work either. Um,
Okay.
Yeah, I know for 10 gig, they have this protocol called XAUI or XAUI, which is four lanes at 3.125. And that's a PHY attached protocol. So if you have your FPGA or whatever, you can go out with four lanes, 3.125 to the PHY chip. That'll then repack it into one lane at 10.
Mm-hmm.
Um, I don't know if there's an equivalent for 25 gig Ethernet, like a four lane version. I know they have a 25G AUI, but that's like XFI. It's the same rate. So 25G AUI is one lane at 25 gig, right? The XFI is one lane at 10 gig. So yeah, that doesn't really help very much if you're trying to run with lower speed SerDes. Um, so the real problem with a lot of these serializers is they're all intended for self-clocking, embedded clocking type stuff. So if you have two lanes that are transmitting, they're not necessarily going to be aligned with each other. So you can't even get like a bit mux and put them together, or on the receive side take it apart unless the protocol is specifically designed for it. 100 gig is a totally different story because 100 gig uses 20 virtual lanes internally. The virtual lanes are then bit muxed together. And because the lanes are bitmuxed, it then means you can do bitmuxing, on the physical lanes, and it works.
Okay.
So you can take 10 gig and with relatively simple logic, repack between 10 lanes and four lanes and two lanes and whatnot, just by reshuffling the bits. And it works because at the other end, you're not just looking at the physical lanes, but you peel it apart. So that's actually one of the things that I realized after I learned a little bit more about how 100 gig works. It's like the first time I was looking at Xilinx's core, I'm like, well, why are they running the transceivers in 80-bit mode? Like, why don't you run them in 64-bit mode? That would make a lot more sense. It's a much nicer number. But then eventually I realized, oh, they have five virtual lanes on each physical lane, and 80 is divisible by five. So on every clock cycle, they're getting 16 bits on each of the 20 virtual lanes out of the transceiver because they're literally just taking the first 5 bits, and that's one bit to the five lanes. The next 5 bit, that's the next bit to the next five lanes, so on and so forth across all the lanes. Um, yeah, so you can do that for 100 gig because it's specifically designed to support it. But 25
Mm-hmm.
gig is just it's only designed for one lane. So
Right.
yeah,
Right.
and even something like PCIe, the lanes all operate differently, and the bonding is done at the symbol level, right? So the striping and bonding is done at the symbol level across the lanes. I can't remember if it's individual bytes or 32-bit blocks or whatever it is, but yeah, the protocol is specifically designed to support running across multiple lanes, right? And even you take a look at something like I guess I need to remind myself of how so there's an old version of a 10 gig Ethernet called 10 gig base X, which runs
Mm-hmm.
four lanes, 3.125 gigabits per second. It's basically the same as XAUI, except you go over a DAC instead of, to a PHY chip. And
Okay.
XAUI, it's 8B, 10B encoded XGMII. And I can't remember how the lane alignment works, but they send alignment markers periodically to bring the lanes into alignment. So that you have to do additional stuff at the protocol level to support, multiple lanes um, to do it properly, right? It's got to be designed with that in mind. So yeah, there's not much you can do if you have a K25 SOM that only supports 12 and a half. Well, okay, let me put it to you this way. If your goal is just to connect the K25 SOM directly to a 25 gig port, that doesn't really work. If your goal is to take a
Right.
device that has two lanes at 12 and a half and to connect that to a 25 gig link, my suggestion would be to use an FPGA like a KU3P, which can have 12 and a half gig on one end and 25 gig on the other end. And then you can implement whatever oddball protocol you need to merge those two lanes together and repack everything in a way to get it out the door 25 gig, right? So maybe you would
Right.
need to, well, so one, you couldn't do it at 12 and a half. You'd have to go faster, right? Because of you have to have enough overhead for the whatever line code you're using. But then two, you would have to have some sort of a line code that actually lets you do that repacking and put everything back together properly at the other end. So I'm not sure exactly what that
Right.
would look like, but you would have to have alignment markers and other stuff that would have to be implemented. Um, so
Right.
it's not a trivial thing to do. And
Right. Right.
by the time you're dropping down a KU3P FPGA to do that, well, you might as well just use the KU3P FPGA in the first place, right?
Right. Right. Right.
So, yeah,
Okay. Thanks.
yeah. Unfortunately, ultimately, what it comes down to with those things is Xilinx's marketing guys are like, we can't compete with ourselves. These are cheap modules. They can't support 25 gig. Because if somebody needs 25 gig, then they got to buy a more expensive module. So, yeah. What can you do? Were you just wondering, or did you want to do 25 gig out of one of those for some reason?
No, I was reading about it, and then uh I was thinking, like, why didn't they put like SFP28 on the board or something like that? Like, why there exists no board with SFP28? Because they are all 10G modules, right?
Yeah.
I mean, only one board, that is KR26, right?
Yeah.
Sorry, 260. And then I remember that you worked on, I think you guys made your own boards, right? Previously. And I was wondering whether you
Yeah,
did that.
we made a couple boards. Yeah. Yeah, so on our boards we put down, I guess on the latest one we put four SFP pluses. Two of them wired to two of the transceiver channels and two of them wired to the LVDSIO on the FPGA. So those only support 1 gig. Um, but yeah, no, the real wrinkle is that we also need PCIe, right? And PCIe also has to use some number of those series lanes. So 2 lanes for PCIe, 2 lanes for Ethernet, and then you got to do some funky stuff with the PLLs in order for things to interoperate. So it's easier if you only need to support PCIe Gen 1 and 2 because that uses the CPLLs. But if you got to do PCIe Gen 3, then you need a QPLL. And now you have to use one QPLL for Ethernet, one QPLL for PCIe, and everything's got to be hooked up just right. So took a few tries to get the kinks worked out of it, but we
Those
did
modules are
finally get
not
it
cheap
working.
either.
Which
Well, those, I think they are expensive. They are like $500, right? The K26 SOM
I thought they
module
were like
each.
350 or something.
Yeah, yeah, could be, yeah,
But
around that,
but but the
400.
thing is, considering the size of the zinc, right? If you were to buy just the bare part, it'd be like $1,000 or something, right? Or even more
Hmm.
than that. So yeah, they are kind of
Hmm.
expensive, but they are actually a decent value, you know, considering. And I mean that SOM also has DRAM and other stuff on it. It's not
Hmm.
just the yeah,
Right,
not just the FPGA. So you think
right.
about, okay, if you're going to put the FPGA and the DRAM and eMMC and the voltage regulators all down on your board, right? How much is that going to cost?
Yeah.
I guess I have my KR260 right here. I was testing relatively recently testing the Ethernet ports relatively recently. Yeah, I think the main annoyance about these things is the very high density SOM connectors are kind of a pain to deal with.
Yep.
Like if I was going to assemble a board myself, I wouldn't use one of these. But then again, I don't know what I would do. I think when you get to these kind of high pin count, high density FPGAs, the only option is to get them assembled by somebody that knows what they're doing and has all the right equipment. Um, Otherwise, yeah, you're going to
I,
be
I,
wasting a lot of money on respins.
my KR260 got fried. I think some of the USB component, like I think some sort of uh protection circuit behind USB kind of got shorted. And now
Uh-oh.
the Linux doesn't boot in that because I think Linux while booting, it it gives an error. Uh,
I
that
have a question for you. Is
Yeah,
Vivado running when you're trying to boot Linux?
no,
You sure about
Because
that?
what do you mean by Vivado running? So, like in the PL, is anything running?
Do you have a cable plugged into the JTAG/UART port?
Yeah. Yes.
Unplug it. Try again.
Okay.
There's a
Okay.
bug. I
Okay.
don't know where it is. I don't know what the heck the problem is, but if the hardware server is connected to the FPGA, Linux does not boot.
Really?
Yeah, I don't know where the bug is. It's freaking stupid. But yeah, it doesn't work. So I've resorted to whenever I need to have that cable plugged in, I plug a JTAG cable in here. Nothing plugged into it, but I just
Right.
plug the JTAG cable in here because there's
Bypassing the
the way this
FPDI chip.
connector so the way this connector is wired, there's a mux and it detects when there's a cable plugged in based on one of the ground pins and it disconnects the JTAG chain from the FTDI chip on here. So just by plugging in a Xilinx JTAG cable in here, it will isolate the JTAG chain from the USB connector on here. So then you could use the USB UART and actually have the thing freaking boot properly. That's the
Oh,
hack that I discovered.
right.
Because yeah, I ran into the same thing. I'm like, I got the board, but Linux does not boot. I'm like, what the heck? And then I can't. I think somebody might have mentioned something about how that could potentially be an issue. I unplugged it, it booted. I'm like, you freaking kidding me? I'm like, you're freaking kidding me because I wanted to see the console messages while it was booting. But
Right.
yeah. So then I realized, oh, if you plug a JTAG cable in there, then you're good. And you can probably short across those pins too if you want to do the same thing, just temporarily. Um, but yeah, it's kind of annoying.
Yeah,
Yeah, so
luckily I had
I
a
don't know if it's a problem in the hard bootloader on the FPGA or if it's a problem in Linux somewhere or if it's a problem in Grub or I don't know. But
yeah,
whatever.
luckily
It's
I had a KV260 and then things worked out there. So I thought, okay, let's just for time being
yeah.
work on
Well,
there
try
and
that. It's possible you got something else going on too, but I just know that's I've had a problem with that in the past.
right.
Um, and yeah, it just if the hardware manager is running and makes any attempt to talk to the damn thing while it's booting your host. So yeah, why that is, I don't know, but I have noticed that. I would have hoped that they would have fixed the bug by now, but I don't even know where it is. So I don't know who to report it to. Right? Is this a Xilinx problem? I mean, I guess Xilinx hopefully would at least crack down where the problem is, but I guess that's asking too much. Also, speaking of Peta Linux, have you heard that they're discontinuing Peta Linux?
Yeah, yeah, yeah. They are moving to Yocto
Yeah,
Yeah,
I mean,
based
Peta
yeah.
Linux
flow.
is a wrapper around Yocto, I think, right? So,
Yeah, yeah,
Oh,
yeah, yeah.
yeah,
well, yes and no. It's much more complex than that. Too complex.
yeah,
So
yeah. I mean,
I'm kind of happy with that decision actually.
yeah. No,
But
I
then
think so. I think you're right about that. Yeah.
but then how do they kind of do the compatibility between the Vivado versions, Vitas version, and then some version that Yocto is working on, right? So there
They
has to be
no, they are doing that through the Yocto layer system. Yeah,
right.
actually, it exists also in Peta Linux, but it's kind of masked, you know.
Hmm.
You don't use it very regularly in under Peta Linux. But what you will have to do is you will download Yocto, normal one, and then you will import your Xilinx meta in a way. And normally, they have, from what I saw, they imported some tools that they had in Peta Linux inside their meta Yocto. And then
Hmm.
it will do the same. So, but you will use standard Yocto tools rather than their Peta Linux stuff. They do a lot of strange thing. At least me, I'm used to use Yocto, and so they do very bad things in Peta Linux. So
Oh,
things
what's new?
are so I'm kind of happy with that.
Yeah,
And
no, I mean, I think the closer they can stay to upstream, the better.
yeah,
So yeah, by using the upstream pay to Linux, that's going to be better for everybody. But yeah, it's
yeah,
yeah,
yeah.
it will take some getting used to.
And
because
also they will use they will. I hope that they will move faster. Version to version.
Hmm. Yeah, that would be good. The other thing that would just be really nice is to be able to put just a regular Linux installation on these things without having to need like, the Xilinx Linux distribution. But hey, can I just put Ubuntu for ARM on here? That would be nice.
Oh, I think it's not that difficult because the Ubuntu stuff is just the userland. So
Right,
once you have the DT the device tree and the Linux that you can compile for each platform independently, then
right.
off you go. You can. I
but
think
then but then there is also this DT, the overlays, right? Device tree overlays and stuff. So wouldn't
yeah,
they?
Well, so that's kind of the whole point of the device trees is that it's independent of Linux, right? It's
all right.
like basically before device trees, how would you target a specific SOM? Like header files and custom C code, right? It's a
Yeah,
gigantic pain in the butt. You'd have to like modify the kernel. You gotta need patches and all this other crap. But
and
with
it's
the
still
device
actually
tree,
it still exists for some architecture.
well, right, yeah.
Yeah.
Yeah, so the idea with the device tree is that it kind of peels away all of the architecture specific stuff, and then you have this just metadata in the device tree, and then Linux can look at that metadata and figure out what to do. So
Mm.
I think I'm not super familiar with the boot process of these things, but my understanding is that the device tree is kind of owned by the bootloader by Grub or Xboot, U-boot. There we go, U-boot,
U-boot.
and then it
Yeah,
gets handed off to the kernel by U-boot. So the kernel doesn't
Yep.
even need the device tree itself. Like it's not built into the kernel. It's not really part of the distribution. It's in U-boot
you
on a
actually
different partition.
you can do that if you want.
Well, you can, but I mean, the point is that you have one partition that has U-boot and the device tree. That
Yeah,
starts first, and then it boots Linux on a different flash partition and says, "Hey, here's the device tree. Now have fun," right? And then at that point, it's
right.
Linux. But the idea is that that partition with Linux, it doesn't need to know the device tree. It doesn't need to know anything about the platform that it's running on,
Yep.
potentially. I mean, you can certainly add stuff if you have config files. Anyway, the
Hmm.
point is that you can separate if the whole system is built properly. So in this case, I don't know if it's built properly, but it sounds like it
Yeah.
probably isn't. But that's kind of the ultimate goal. Now, I still think it's a completely hackish solution because you don't need that on like x86 systems, right?
Mm.
You take Linux, you pop it on there,
Yeah.
you're done. You don't need
And
to have a partition that has all this additional metadata
you,
crap.
you
Or I
say
guess
that because you never saw how it worked in
yeah, probably
in the
because it's
X14.
probably because that's part of the firmware on the motherboard or something. Yeah.
Yeah, there is a
Um,
firmware on the motherboard, and there is a huge pile of hack accumulated over time.
I see.
When the Linux it tests something, it reads some place in memory to deduct some facts that are something right and something sometime wrong, and so no, it's not perfect all the time. It's
Right. Well, it's not
it's
perfect, but at least like if you would install Linux on a computer, you generally it's just x86 or x64, pop it in, you're
yeah,
done. And but if you go
yeah,
to like I don't know if you've ever used like OpenWRT, right? You go on there, there's like 5,000 freaking builds. It's like,
yeah,
why?
yeah, right, of course.
Why can't you
Maybe-
just have one? And then yeah, okay, great, you have a bunch of config files, but
yeah.
yeah,
Yeah.
not great.
But basically, the PC is just the CPU, the CPU with some basic stuff around that are more or less compatible for each platform, and then it's all on PCI bus.
Right.
If you do an LSPCI on a computer, you see a huge pile of stuff,
Yep.
especially on a server when
Yep.
you have sometime up to 50 peripheral, and then you have auto detection in a way.
Yeah.
Yeah, no,
Auto
PCA is
discovery,
great
right?
Auto
because you have
discovery.
the PCA config space, right?
But
So the config
Yeah,
space gives you
exactly.
all that information, all that configurability, no matter what's on there. So Yeah, and I guess you could even add like virtual PCIe devices, right? Like a lot of the
Yeah.
root complex integrated endpoint stuff. Yeah, it doesn't really have to be PCIe, right? I mean, but PCIe gives you a nice standardized way to enumerate it. But yeah,
Yeah.
then you go to all of these, like your cell phone. It doesn't work that way. Or maybe
No,
it does now, but
no, it
historically,
doesn't.
no. You just have one big honking address space and you have no idea where anything is. It's like
Yeah.
great, great.
And still on the phone, it's still like this. I mean, if you want to change the firmware of your phone, you have a huge pile of image to select from, and if you miss, if you flash the bad
You
one,
get a brick. Yeah,
But
yeah. Oh, and then
is the
ARM, and then no, Apple is building computers with these CPUs in there. So it's just like, oh, okay, great.
yeah,
but is the reason of not having auto discovery like PCIe bus on an ARM chip was the argument like the power efficiency and things like that? Does
It
PCI
saves
take too much power?
transistors. It takes a couple
Uh,
extra transistors to implement that. We don't
yeah.
have room for those extra transistors. We can't afford the couple of microwatts it would consume, or
And
nanowatts, or
also, maybe
whatever.
it's some kind of historical stuff as well. I think also. Because ARM they used to add a lot of small peripheral at
Yeah, I mean,
some
so so
place in
so
the
so the thing
aerospace.
with the thing with ARM is that it has really developed from being a microcontroller, right?
Yeah,
ARM was
yeah,
initially like microcontrollers, and then they started building more powerful cores. But when they started building more powerful cores, they didn't redesign the overall system architecture, right? They're still built like a microcontroller. They still have the address space
yeah,
laid out like a microcontroller. Everything
exactly.
else is based out of this just flat address space. And PCIe is not a flat address space, right? You have the config space, which is based on where the devices are physically located and whatnot, and then you can remap the flat address space however you want, more or less. Um, and you can do that dynamically, right? You can go through the config space and figure out what devices are there, figure out how to enumerate it, figure out how to lay things out, and you can do this in a standardized way and figure out where everything is, all of the relative locations between the components and everything. But would you just have a flat address space and no separate config space, you're hosed, right? And ARM has never had
Mm.
anything like that. So I mean, I guess maybe that's one of the things that Apple has been doing is to try to bring some of that to ARM. I'm not even sure about some of the ARM server vendors, like Ampere, I think makes
yeah,
is Ampere the chip or Ampere the company? I can't remember, but they
it's
make they
it's a
make
com
server chips as
yeah.
well that are ARM based, and I wonder about those, right? Are they still using freaking device trees on those, or did they actually invent something more modern? Um, that's more
Mm.
extensible.
You have some ARM platform with UFI,
Right.
like
Well,
like
okay.
like
So
on
I
the
guess
PC. So
right. So I guess UEFI, does that basically just replace U-boot effectively? So you have
yeah,
this
kinda.
yeah,
Yeah,
okay.
you can. Yeah. And actually, on one platform I use it's NXP. You have the choice between U-boot and UFI bootloader.
Okay. And then when the UEFI version boots, how does it hand stuff off to Linux? Does it do the device tree handoff, or is there actually some sort of PCIe
It's kind of
style tree?
it use an equivalent of grub like you
Right,
have on your
okay.
PC, and then it loads the device tree.
Okay. So
Often
they're
it's
still using the device tree. Okay.
yeah, but it's inside. It's a very reduced one,
Hmm.
a basic one, if you want, which is embedded in the kernel itself. You know,
Hmm.
at the end of the kernel, and the kernel read it and say, okay. And actually, in the X, I think in the Intel AMD world, there is also some kind of device tree. It's just that it's identical for all computers.
Hmm. Well, I know there's ACPI, and I think that is kind of maybe somewhat similar, where various
Yeah.
hardware information is exposed. I don't know if this is like just a data structure or if this is
Yeah,
queried somehow.
ACPI was kind of a table to
Yeah,
describe some quirks in a way.
yeah,
And UEFI is more based on some kind of routine that you can call when the kernel starts.
right. Okay.
Okay, to configure things or to detect stuff, or and with more or less standardized. So that's what I understand, and that causes sometimes a problem as well because this kind of core needs very controlled environment when you call
Hmm.
the stack and all of that. And sometimes when it's not very well handled, you can have crash due to that. So you say,
Yeah,
for
it's
example,
not
that
optimal.
on the computer it works most of the time, but the problem is most of the time. Sometimes you have some issues with some new computers, for example, on Linux.
Hmm.
That when you have something like the battery that doesn't work or the screen that doesn't light up because the correct routine is not called,
Hmm.
and so
Oh,
what
what
actually
about my Dell laptop that occasionally doesn't want to turn itself off? Right?
yeah.
I go to shut it down and it immediately boots itself back up. I go to put it to sleep and it immediately wakes up again. I'm like, ugh.
Yeah, yeah, that's the kind of thing. And what Linux does in that is that they analyze how Windows works and they try to mimic how Windows works because we are sure that at
Oh boy.
least the makers it works under Windows, you know. So if you
Hmm.
mimic how it works, then okay. But most of the time they don't follow the UFE standard because
Hmm.
if you
Even if the
do,
UEFI says you're supposed to do XYZ,
yeah.
they do
Yeah, yeah,
XYD or something, and
yeah.
then it's like,
Oh,
okay.
oh, sometimes it's in the ordering of stuff, or you call
I
one
see.
function between another, and sometimes yeah, it's a
So
nightmare
it's
in
the kind
fact.
of thing where, like, okay, technically it should work either way, but somebody makes an
Mm.
assumption at some point about the ordering, and if you do it in the wrong sequence, then
Yeah,
everything gets all messed up. Uh,
exactly.
great.
So yeah, it's not that simple, even
Yeah.
at
So I
the
guess I
PC
guess
world.
that's one of the problems with ARM devices is there's such a massive variety of them that there's no way that you're going to be
Yeah,
testing on every single one. Whereas
no.
this, how many different chips does Intel make? Well, yeah, it's a lot, but there's only one company making them, and you can get those same chips in lots of
And
different
actually,
systems.
they are very similar also. I mean, the
Well, yeah,
basic.
yeah, yeah. Within a line, right? Different numbers of
Yeah,
cores, different clock frequencies,
yeah,
or whatever, but they're all going to be basically the same. And the
yeah.
chipsets, same thing. Intel makes a chipset too. So, how
So
much
yeah.
difference is there even between 10 different computers from 10 different
Mm.
manufacturers if they're all using the same CPU and the same chipset? Well, okay, they might have different
Mm.
firmware bugs, but
Yeah, and it does. But yeah, it's not that. But actually, I'm very surprised that Linux works that well on ARM with this difference because on some platform you can have, for example, on Raspberry, you can have one kernel and multiple, device tree overlays and all of that, and it still works quite well actually.
right,
So
right,
it's
yeah.
not that bad.
Well, I guess they've had a lot of years now to work some of the kinks out. So
Yeah.
lots of years and
Yeah.
lots of devices. Well, I mean, the other thing is that, it has to run on all these different phones and such, right? You think, what do they have to do for Android to make a Linux kernel
Yeah.
boot on all these devices?
So
Lots of
I think the
opportunities
Android stuff
to,
is the actual nightmare on that.
well, yeah, okay, fair
Because
enough.
because yeah, they really did some yeah, again, very bad stuff in Android.
Jeez. Go figure. Well, I mean, I guess that's one of the things. Like, if, from Apple's perspective, in some sense, they're starting from a clean slate. I mean, in some sense, they aren't, but potentially they can do some things. I mean, Apple does things their own way, right? That's kind of how they do
Yeah.
things. But they can potentially solve some of these issues because they don't care about backwards compatibility. They're building their own chip. Um, so they can get stuff least with older versions of Linux or older versions, at least with other ARM systems, they didn't really care too much about that. Obviously, they got to make the x86 stuff work, but that's
Yeah,
a
and
slightly different ball game probably. They just need to run the executables. They don't need to boot an x86 OS on there. So hopefully they can clean up the bootloader stuff and make that work a little bit nicer. But did they actually do that? I don't know.
Okay.
All right. Does anyone else have any questions or comments? Or certainly had quite a things got a little bit derailed talking about how various things boot, but you know, hey, why not?
Yeah, absolutely.
Going once, going twice. All right. I guess
Fine.
we'll adjourn for today, and we'll talk to everybody next month probably, unless something else comes up. I don't know. If anybody has any other questions or comments or anything, you know where the Zulip is. So,
Thank you very much.
all right,
Thanks.
sounds good. Well, talk to you guys later.
Bye.
Thanks a lot for the meeting.